Welcome everyone to Dr. Carmenatty's channel. Today, we're embarking on a critical journey into the heart of artificial intelligence and machine learning. These technologies are no longer science fiction. Developers have embedded these robust systems in our daily lives, from the spam filters in our inboxes to the complex algorithms that guide autonomous vehicles. Great power brings great responsibility, and in the world of AI, this responsibility means understanding and mitigating the security threats that can turn powerful tools against us. In this video, we will explore the Open Web Application Security Project, OWASP, and the project's top 10 security risks for machine learning. We will dissect each threat, understand each threat's potential impact, and most importantly, discuss how our community can defend against these threats. So, whether you're a seasoned developer, a curious student, or someone who wants to understand the technologies shaping our future, you're in the right place. Let's begin our exploration of the OWASP Machine Learning Security Top 10. Our first threat is input manipulation attack. Imagine having a highly advanced security camera that utilizes facial recognition to grant access to a facility. An attacker, armed with a pair of specially designed glasses, can trick the camera. The camera then incorrectly identifies the attacker as an authorized person. This scenario is the essence of an input manipulation attack, also known as an adversarial attack. Attackers subtly alter input data to deceive a machine learning model. This deception leads to the model making incorrect predictions. The alterations are often so minor that the human eye cannot perceive them, but to the AI, the alterations are a clear signal to misclassify the input. To defend against input manipulation attacks, we must build more resilient models. One effective technique is adversarial training, where we intentionally train our models with manipulated data. Adversarial training teaches a model to recognize and distinguish between malicious and legitimate inputs. Additionally, implementing robust input validation is crucial. When we check all incoming data for anomalies and reject anything suspicious, we establish a strong first line of defense against input manipulation. Next on our list is data poisoning attack. The quality of data used to train a machine learning model determines that model's quality. But what if an attacker intentionally corrupts the training data? This event is a data poisoning attack. An attacker can inject malicious data into a training set, causing the model to learn incorrect information. For example, an attacker could train a spam filter to identify legitimate emails as malicious, or manipulate a medical diagnosis model to provide incorrect diagnoses. The consequences of such an attack can be devastating. To protect our models from data poisoning, we must secure our data pipelines. This security process starts with data validation and verification. We must thoroughly check all training data for inconsistencies and anomalies. Secure data storage is also non-negotiable. Encrypting our data and implementing strict access controls can prevent unauthorized modifications. By continuously monitoring our training data and validating our models with clean, separate datasets, we can ensure the integrity of our AI systems. Now, let's discuss model inversion attack. Imagine a machine learning model as a black box. You provide an input, and the model produces an output. But what if someone could reverse engineer that black box to see the information inside? A model inversion attack does just that. By analyzing a model's predictions, an attacker can extract sensitive information from the training data. For example, an attacker could invert a facial recognition model to reveal the identities of people in the training set. Or an attacker could compromise a model trained on medical data to expose patient records. To mitigate this threat, we must control access to our models and the model's predictions. Implementing strong access control mechanisms can prevent unauthorized users from interacting with a model. Input validation also plays a crucial role here because proper validation can prevent attackers from feeding a model malicious data designed to extract sensitive information. Furthermore, by making our models more transparent through logging and providing explanations for predictions, we can detect and deter model inversion attacks. Regularly retraining our models with new data can also help keep the information that an attacker could leak from becoming outdated. The fourth threat we'll examine is membership inference attack. This attack also targets the privacy of the training data. An attacker can use this technique to determine if the training process used a specific individual's data. For a model trained on sensitive data, such as financial records or medical histories, a successful membership inference attack can have severe implications for privacy. To counter this threat, we can employ several techniques. Model obfuscation, which involves adding random noise to a model's predictions, creates more difficulty for an attacker trying to infer information about the training data. Regularization techniques can prevent a model from overfitting to the training data, thereby limiting the amount of information an attacker can extract. By reducing the size of the training data and removing redundant features, we can further minimize the attack surface. Our fifth threat is model theft. A machine learning model is a valuable asset. The model represents a significant investment in time, data, and computational resources. Model theft is the unauthorized access and use of a trained model. An attacker can accomplish model theft by reverse engineering the model's code or by gaining access to the training data and algorithm. The consequences of model theft can be severe, including financial losses, reputational damage, and the loss of a competitive advantage. To protect our models from theft, we must treat them like any other valuable asset. Encryption is a powerful tool for preserving a model's code and data. Access control is also essential. By implementing two-factor authentication and other security measures, we can ensure that only authorized personnel can access a model. Regular backups, model obfuscation, watermarking, and even legal protections, such as patents, can all play a role in a comprehensive model protection strategy. The sixth threat on our list is AI supply chain attacks. The machine learning development process is a complex ecosystem of tools, libraries, and platforms. An AI supply chain attack targets any of these ecosystem components. By compromising a popular open-source library or a third-party data provider, an attacker can inject malicious code into a wide range of AI systems. These supply chain attacks are hazardous because they can be challenging to detect and have a widespread impact. To defend against AI supply chain attacks, we must be diligent about securing our development environment. This diligence means verifying the integrity of all third-party packages and keeping all of our software up to date. We should only use packages from trusted and secure repositories. By securely deploying our ML infrastructure and implementing strict access controls, we can create a more resilient and secure AI development pipeline. Now let's explore transfer learning attack. Transfer learning is a powerful technique that enables us to utilize a pre-trained model and fine-tune it for a new task. However, an attacker can also exploit this learning process. In a transfer learning attack, an attacker trains a model on a malicious dataset and then transfers that malicious knowledge to a target model. This transfer can cause the target model to behave in undesirable ways, such as misclassifying data or revealing sensitive information. To mitigate this threat, we must be vigilant about the data we use to train our models. Regularly monitoring and updating our training datasets can help prevent the transfer of malicious knowledge. We should only use secure and trusted datasets. Implementing model isolation, which separates the training and deployment environments, can also help to prevent the transfer of malicious knowledge from one model to another. Our eighth threat is model skewing. Developers often design machine learning models to learn from user feedback. However, an attacker can exploit this feedback loop. In a model skewing attack, an attacker manipulates the feedback data to cause the model to behave in an undesirable way. For example, an attacker could bias a content recommendation engine to promote specific content, or manipulate a fraud detection system to overlook certain types of fraud. To defend against model skewing, we need to protect the integrity of our feedback mechanisms. This protection begins with robust access controls, ensuring that only authorized users can provide feedback. We must also verify the authenticity of all feedback data and clean the data before using it to update our models. By implementing anomaly detection and continuously monitoring the performance of our models, we can detect and prevent these attacks. The ninth threat we'll discuss is output integrity attack. In an output integrity attack, an attacker modifies the output of a machine learning model to alter the model's behavior or cause harm. For example, an attacker could manipulate the output of a medical diagnosis model, resulting in incorrect patient treatments. An attacker can do this by intercepting the model's output and replacing the output with a malicious value. To protect against output integrity attacks, we need to secure the communication channels between our models and the users of these models. Using cryptographic methods, such as digital signatures, can help verify the authenticity of the results. Securing communication channels with protocols like SSL/TLS can prevent man-in-the-middle attacks. By maintaining tamper-evident logs of all interactions, we can detect and respond to these attacks. Finally, we come to model poisoning. Model poisoning is a direct attack on the model itself. An attacker manipulates the model's parameters to cause the model to behave in an undesirable way. An attacker can achieve this manipulation by modifying the images in the training dataset or by directly adjusting the model parameters. The result is a poisoned model that will produce incorrect or malicious outputs. To defend against model poisoning, we need to design robust and resilient models. Regularization techniques can help prevent overfitting and reduce the chances of a successful attack. Utilizing robust model architectures and activation functions can also provide benefits. By using cryptographic techniques to secure a model's parameters and weights, we can prevent unauthorized access or manipulation of these parameters. And there you have the OWASP Machine Learning Security Top 10. We've journeyed through the dark alleys of AI security, from the subtle deceptions of input manipulation to the brazen theft of an entire model. The threats are real and the stakes are high. But as we have seen, for every threat, a defense exists. By understanding these vulnerabilities and implementing the mitigation strategies we've discussed, we can build a more secure and trustworthy AI ecosystem. The future of artificial intelligence is in our hands. Let's work together to ensure that this future is safe, secure, and beneficial for all. Thank you for joining us on this vital journey. If you found this video helpful, please give the video a thumbs up, share your thoughts in the comments below, and don't forget to subscribe for more content on the cutting edge of technology and security. Until next time, stay curious and stay secure.